Okay, off we go. So, about the computer. Oh, no, real quick, don't forget attendance quiz. Right, so 2 minutes, clock's ticking, right? Make sure to get that in there. Again, 11:02, the quiz disappears. Make sure you get this number inputted. Make sure you get it indicated that you have 1 out of 1 points awarded to confirm that it's been actually submitted. Okay. Oh, and then while I'm at it, let me TA for the course, one of the TAs that is, the one that's holding TA office hours, Spencer, so I talked about him in an email that I sent y'all. He says that attendance has been very low at his office hours. Now, you're not required to go, right? But pretty great opportunity there, right? This is a math grad student. He's very good. He strikes me as the kind of person who would be good at explaining things. Free opportunity for help. Hope everybody will capitalize. Okay, lastly then, about the computer. I have the suggestion that if I leave it plugged into power, that might reduce the likelihood of unexpected, mistakes, yeah.
What are the TA office hours again?
Oh gosh, I don't remember. They're posted on the class website, course website. So if you go to class website and then click on course website, and then in the how to do well in this course section, there's a thing that says office hours. So yeah. Okay. So I've got it plugged in. Hopefully that will allow it to function. We'll see. Proof will be in the pudding. Okay, picking up where we left off, we're into chapter 2 now. Talk about multivariable functions. And I want to start off with a quick definition of what a function is. Now, do note we're in one of these sections where this is, it doesn't really quite make the cut for spending full class time on this stuff. There's a lot of little details here. I think this is pretty readable, right? But the big things, as usual, I do want to hit. A lot of people misunderstand what a function is. A lot of people think that a function is a formula. And it's not only too narrow, but it's also just not enough. A function is actually a trio. It is a group of 3 things. So a input space, an output space, and then we will broadly call the rule of assignment. This is what is typically thought of as the formula, but it might not be a formula. It doesn't have to be an actual formula. So the input space, what I like to call the input space, casually, where you're getting your inputs from, right? And then it has to have an output space, again that I described casually. Where do the outputs go? Right? The more common terms are domain and target. That's what I'll be using going forward. So be on the lookout for those terms. The term target, sometimes codomain. Okay. All right. So just a couple of examples. Y'all remember the natural log function, and the natural log function is defined on this domain of positive real values, and the output values could be any real numbers. So there you go. So the most important thing about this example, I think, is the notation. It's a very common notation to describe a function. You have the function name, then a colon, and then domain, and then an arrow, and then target. And this, aside from being a standard notation, kind of conjures the right image of, well, stuff is coming out of here and then going, as suggested by the arrow, going into it. Okay. All right, so heads up, I'll be using that notation a lot. Here are a couple other examples. We've got F, G, and H. And what I like about this example is we have here 3 functions. All have the same formula in, again, casual speaking. So the same rule of assignment. Namely, whatever input you give me, student of some category, the output value of all of these functions is the same. It's that student's ID number. So how are these, in fact, different as functions at all? They all give you the same output values. Well, they have different domains and targets, and that makes them importantly different functions. And we're going to see why with a kind of an example we'll do in just a quick moment. Okay, so a little bit of terminology here. This word image just means the actual outputs, not to be confused with possible allowed outputs, right? So the distinction here, let's look at this function right there. F of x equals x squared, real numbers in, real numbers out. Well, I allow any real number to come out, but notice not all real numbers actually do come out, right? Only the non-negative real numbers can ever actually come out of this, right? So the target here, the allowed outputs, is all real numbers. The image, the set of actual outputs, not the same set. Okay, so bear in mind that distinction, and I am sorry to report that sometimes, actually way more often than should ever happen, the term image and the term target get conflated. That's not good. They are importantly different. Okay, all right. Okay, a little bit of terminology here. When you have something go into a function and something comes out of a function, the output is called the image. Suit yourself as to how you justify that term. I think it again kind of conjures this idea of something going into and then landing on the target, somewhere in the target. But anyway, the output value itself is called the image of the input, and turning that around, the input that gave that output is called a pre-image of that output. So terminology, very useful. You will notice my use of a instead of the, and that's because there might be several inputs that all give the same output. Right? So it could be a bunch of these. Any single one of those pre-images is just a pre-image. Okay, a little bit more terminology, and again, I'm going fast through this because mostly this is stuff y'all can read. But we need to be clear on these ideas here onto one-to-one and invertible. And also sometimes going by these terms, surjective, injective, and bijective. So roughly speaking, it gets to, given an output, how many corresponding inputs do we know there must be? A function is onto, aka surjective, such as this one here, if for every point in the target, every possible output, there is at least one pre-image. You can see that's the case here. So every one of these target points has at least one pre-image, and in fact, this one has two pre-images. On the flip side, injective means that every point in the target has at most one pre-image. Such as, for example, this one, right? Every point in the target might have one, might have zero, but never more than one pre-image. Okay, and then bijective means exactly what it sounds like. It's both of the jectives. Right, so injective and surjective. And if you draw a picture of a function that is both injective and surjective, I'm just going to say, persuade yourself from the picture. If every output has exactly one corresponding input, exactly one pre-image, then you can invert this function. You can say, instead of thinking of this as a function where the arrows go that way, you could just say, hey, let's just turn those around. That then would be the inverse function. It's just undoing. If you think about it, you have to have exactly one pre-image to be able to do this. If there were point, like look at this one here. Look at this point, right? This point of the target, right there. It doesn't have any preimages. How can I invert this function? What would be the value of the inverse of this function for that point? I got nothing to go with, right? And then you look at this point out here. Well, it's got 2 preimages. Which one do I pick? There is no clear, unambiguous inverse for something like that. So you got to have both of the objectives, right, to be inverted. All right. Okay, so a couple of examples. Now again, still, we're going to go quickly through all this stuff, so make sure to read all the details, make sure to think it all through. Very commonly misunderstood fact. A lot of people would look at this function, right, f of x equals x squared. Now, of course, I can put in any real number, no problem. Of course, I could, until I do some analysis to actually understand the outputs, I would expect to get real numbers output. I mean, do I get all the real numbers or some of the real numbers? That depends on the specifics of the function. But I could call it a function from R to R. Real numbers go in, real numbers come out. Kind of no problem as a function. And that function's not invertible. Common misunderstanding. A lot of people think square root is the inverse of this function. This is not true. That function's not invertible. In both ways, right? It's got both problems. What's the inverse function of this applied to 9? Is it 3 or negative 3? Both of them are preimages. Right? It's a problem. Oh, what would the inverse function of this be as applied to negative 5? You got nothing. Right? So that's just not an invertible function. So you've got to decide how to toy around with the domain and the target to make this invertible. There is more than one way to do this. This is the standard way to do it. This is what I'll call the invertible square function. This function is invertible. It is not defined for all real numbers. It's only defined for the non-negative real numbers. Likewise, I am not going to allow any real number to be the output. I'm going to restrict the target to be just the non-negative real numbers. And as such, we solve both of the problems that we just encountered with the f above. This is invertible, and its inverse, the inverse of that function, is the square root function that y'all are all previously familiar with. And a reminder, don't forget, easy to lose track of this. Let me color code here. The domain there being the non-negatives, the target here is the non-negatives. And that is just another reminder that this symbol here means positive. Just because that's how we set it up. Okay. How we doing? Everybody's happy? Okay. All right, another example, and I don't want to go down the bunny hole of trig, but this is what I'm going to call the invertible sine function. Now, this is not how the sine function is defined in most trig classes. In most trig classes, theta is allowed to be any angle. Here I'm very much restricting that I'm only allowing theta to be, here let me be more careful with my color coding. Only allowing theta to be these values here. And very often people figure, what's the point of restricting the target? The outputs that come out are the outputs that come out. Why do we have to be all fussy about it? Right? Well, I'm going to restrict that here, allowing only these outputs, so that I can then say, and by the way, this function is bijective, aka invertible, and therefore I can talk about its inverse, and that inverse is called arcsine. Arcsine is the function that just kind of goes the other way. Okay, so if you give me one of those blue values, the arcsine is one of those green angles. Okay. All right, so likewise for the other 6 trig functions, make sure you're good with that. By the way, there's a quick little diagram over here. This is the unit circle, not a graph, right? But I find the unit circle to be a really convenient way to think about sine and cosine, certainly. And so a different way to think about the process of taking an angle and getting a value of sine, and then vice versa. Okay. All right. Now this really is just terminology. We're going to be using these terms quite a bit. So heads up. The broad brushstroke that I'll hit on this is that these terms that say something about values, real value, scalar value, vector value, those are talking about the outputs. What kind of critters come out of this function? Are they numbers? Are they vectors? What are they? Are they matrices? And then the terminology down here, variable, is a reference to what types of critters go in to the function. And again, is it a single number? Is it a list of numbers, aka a vector? Is it a matrix? Is it another function, maybe? Right? It's a big world out there. There's lots of ways to define functions and what they take in and what they spit out. So heads up on this terminology. Make sure to read and retain. This business about component functions, again, I think that's pretty readable, but sometimes we just want to look at one component out at a time. And then a quick example. And I like this example because, you look at this term, vector valued multivariable function, and you can intimidate people at parties with that term. That's scary sounding, right? It's a mouthful. It sounds like some really big, sophisticated stuff, and there is the sort of suggestion, the vague sense that it must be some abstract, narrow sort of a concept. And that's absolutely inaccurate. Vector valued multivariable functions are just, oh my gosh, there's all over the place. And so just to hit that home, the most trite of water cooler conversations, talking about the weather. And you're talking about a vector valued multivariable function, right? So if you want to talk about the weather, you got to tell me where you are, latitude and longitude. Technically, we have to worry about the altitude because the weather at 10,000 feet is not the same as it is down here on the ground. And you got to tell me what time you're talking about. You're talking about now, you're talking about yesterday, you're talking about 4 hours, what are we doing? Right, so these are the inputs to the conversation. We have to specify what, where and when are we going to discuss the weather, and then the outputs to this are, what is the weather at that time and place? Well, we talk about the temperature, the barometric pressure, the wind speed, the humidity, a bunch of other specifics that we'll call outputs here. So technically, vector valued. Let me do it like this. Vector valued multivariable function. Okay. So that's kind of what this course is about, is studying the calculus of vector valued multivariable functions in different points of view. And so important to observe that they're everywhere. Okay. How do you visualize these things? And first, let me start off with a little bit of bad news. It's not like in single variable calculus. In single variable calculus, the great majority of pictures that you draw to represent functions are exactly the same kind of picture. They're all this construction called a graph. And it's almost universal, not quite, there's a few counterexamples, but almost universal that graphs are how you draw functions that you're doing business with in a single variable calculus course. It's so common that students get deluded into thinking that that's what the function is, and that is how you draw functions, and that's the only option. And again, importantly, critically not true. Graphs are a wonderful construction. We are going to be using graphs a lot in this course, but they are not good enough on their own. We're going to see that momentarily. It is one of many constructions, and here's where it gets a little weirder. Different types of constructions have different geometric interpretations. The way that we're accustomed to understanding graphs, none of that applies when you're using these other geometric constructions. So the kind of sloppy, loosey-goosey take that is kind of, you can get by with in a Calc 1, Calc 2 class, it's not going to work in this class. We're going to need to be much more careful and deliberate in how we interpret and how we create pictures that help us visualize functions. So, by the way, the most challenging part of this is the being careful part. Right? The actual mechanics of the various different pictures we're going to draw are not hard. Right? The resulting algebra is like not even algebra 2 level. It's like algebra 1 level. That's not hard either. What's hard is using the terms correctly, interpreting the terms correctly, and carefully. That's what's really hard about it. So try to keep that in mind. You do have to focus on being careful and strict in how we use and interpret these terms. Okay, jumping on in. What's a graph? I like to start with this example down here. This is the example we're all familiar with. If you have a function like so, now let's take a quick moment to pause. What is the deal with this function? Well, you notice the domain is R1, the target is R1. This is just a function that takes real numbers in and gives real numbers out. Right? Good old Calc 1 single variable function. Okay. Real value, single variable function. Okay, and y'all are accustomed to seeing pictures like this. Again, that's the most common type of picture that we draw. Let's break down exactly the process. What turns that function into that picture? Right? I'm just going to be real careful about it. So what we do, there's different ways to think about this. But if you take the inputs that go into this function, call those the first coordinate, then take the outputs that come out of this function, call that the second coordinate, then these resulting points, x comma y, are points in 2 dimensions. Take a quick moment to recognize how surprising and weird that is. This function is not defined on R2. Right? This function does not take 2 inputs. This function does not give 2 outputs. The domain's R1, the target's R1. Everything's single variable. Why are we drawing a 2-dimensional picture? That's a little weird. It's an eyebrow raiser, right? It's not truly weird, but it's noteworthy. Let's say that. So a point on the graph is a point in 2 dimensions where the first coordinate is the input, the second coordinate is the output. And if you do this for all of the inputs, then of course you get a curve, and that's what we call the graph, and like so. That all look familiar? Here's another way to think about it. By the way, that's what gives rise to this definition up here. This definition, you notice the input might have multiple variables, so there might be multiple inputs. The output might, again, have multiple variables. But in the same way, we're going to say, look, list the inputs first and then the outputs second. And you get a bunch of points now in, n plus m dimensions. And so, how would we draw this graph? Oh my gosh, I don't even know. Right? As I have it indicated here, it looks like we just got way too many variables. Okay, but that's just a definition. Okay, so a different way to think about it, and I think this is a pretty reasonable way to think about it, that we're going to take all of these input values Think of the input values as being the x-axis there in the xy plane. And then think of the function as telling you how far should I take each one of those points and kind of push upward. And this is, I think, useful because if you want to understand, sort of what's the nature of the resulting graph, well, the graph is really just kind of a contortion, sort of a distortion of the domain, right? And so, for example, the x-axis being a one-dimensional curve. Well, if you just kind of, one point at a time, just kind of shove upward or possibly downward, whatever, the results just still curve. Just like the domain is. Okay. Here's a third way to think about it. Also really useful depending on the circumstance. There's a choice involved here. We start with a function. When you have a function, there's an input value, there's an output value for any input value. And maybe we call the inputs x. The outputs that come out are f of x. End of story. Notice I didn't say the letter y. Right, if you have a function, whatever comes in, you do the function to it, that's your output. That's all the function has to do. Right? Making a graph, you can take the point of view that the way you make a graph out of a function is that you say, look, let's look at the output values for any given input. Let's give them those output values a name. We will choose. Again, don't have to do this. Free country, no obligation. But if you want to form the graph, you say we choose to call those outputs by a different variable name. Call it y instead of f of x. And when you do so, this resulting equation, that equation gives a curve, and that curve is the graph. So, different way to think about it. All the different points of view I gave you are equivalent, right? But I think it's nice to have sort of different takes. Yeah?
What is the D represent?
The D?
Like up there in the definition.
Oh, yeah. I was just pointing at, I'm just being fussy. I'm just pointing out that when you have a function, the domain doesn't have to be all of Rn. Your domain might just be some subset of Rn, like maybe your formula isn't defined for certain points or something like that. And so I'm just leaving open the possibility. It doesn't have to be defined on all of them. Yeah. Okay. All right, so let's apply these ideas to our very first multivariable function. Here we go. Function from R2 to R1. All right, well, let's see here. So the inputs are now sort of points in the xy plane. X and y are both inputs. So the input point is point in 2 dimensions. Right? And then you can look at the corresponding output value. The output value is z. And again, if you smash those together, the inputs, of which there are 2, the output, of which there is 1, that gives you then a point on what we call the graph, and I claim that that's a surface now. It's not a curve. It's a surface in 3 space. How can I persuade you that it should be a surface? Well, keep in mind our other take is that the function tells you how far to push upward, right? So you look at our original picture, x and y could be any values, right? The domain is all of R2, so I start with the xy plane kind of being my domain, and the function just tells me how far does each point in the xy plane have to get kind of pushed upward, and so you can sort of imagine the entire xy plane kind of being lifted and sort of curved around, bent, by every point going straight up by different amounts. And since we started with a 2-dimensional surface, wouldn't you expect the result to also be a 2-dimensional surface? Generically. Typically, let's say. Okay. All right. Or, said differently, when you have an equation involving 3 variables, now again, two of them are inputs, one of them is an output, but nevertheless, that's an equation involving three variables, and so that's why we get a picture in three-dimensional space, and typically one equation you would expect to reduce the dimension by 1. So kind of expect a two-dimensional surface. Okay, all right. So now at this moment, you might actually be pretty enthusiastic about this idea. Well, check it out. We get a picture. Check it out. The output values are up, just like they were in single variable. I think we can kind of work with this, right? It's a little hard to draw surfaces in three-dimensional surfaces. Three-dimensional world with a surface containing it, but we're drawing it on a two-dimensional page, right? It's artistically a little tricky, but kind of seems okay. Let's just think about the very next example. Right? What if we're looking at a function with 3 input variables? Well, if you have 3 input variables and 1 output variable, you already have an equation involving 4 variables, and we lose. You can't draw that picture. You can't really visualize that picture. Maybe if you were to, in some weak sense, perhaps, even then, I think it's pretty hard. Right? So basically, thinking about a graph in anything other than the most trivial multivariable type function. This is the most trivial. It's 2 to 1. Right? Anything but the most trivial example, you can't draw the graph. Anybody see why we don't like this? Right? This is we're going to encounter functions with 3 input variables, and we need pictures of some sort to help us understand them. And graph isn't going to do it. Okay. All right. Okay. I've already talked about this a little bit, but we got to be very careful with the terminology. So again, in single variable calculus classes, very often people will point to a picture and say, okay, let's talk about that function right there. Right? Or, in general, people will kind of conflate the terms picture and graph. That's going to be a problem. We're going to draw lots of pictures that are not graphs, that are importantly not this construction. They are not graphs. Some students will conflate picture, figure, graph, and function. And again, you got to distinguish the function, which is an abstract algebraic construction, from the picture you use to draw, get some understanding of that function, because we will have multiple such pictures. You can't have 2 different pictures and refer to both of them as the function. Confusing. Misunderstandings will happen. Unacceptable. So, and then lastly, let me gripe that very often students will conflate the words equation and function. This is another real problem. This is a function. A function is an abstract algebraic operation that takes inputs in and gives outputs out. Right? An equation is a statement. That is an equation. Specifically, what I have highlighted in blue here, this is the equation that defines the graph of that function. That blue equation is not the same as the function. The function is just the abstract algebraic critter itself. So again, be careful about that, yeah.
Could you have a single variable vector value function?
Yeah, absolutely. Yep. And so in fact, here's a great example we've already seen, a parameterization. is a single variable because everything's a function of time, but it's vector valued because it gives you location as outputs, and those can be thought of as vectors. Yeah, it's a great question. Yeah. Yep. Yeah, you can have any number of inputs, any number of outputs. Yeah, totally. All right. Okay. So, heads up on the terminology. Please try to be careful. By the way, let me recognize. I know that this might be the first time that you've faced a serious need to be careful about all this stuff that I'm asking you to be careful about. And I know that means that you have habits built in that are going to be hard to break. And I'm sorry, but you just got to do it. I had to go through the same thing. I can't blame my teachers from single variable calculus. I mean, they were teaching the course as was appropriate. Anyway, given the context, right? But I too, to this day, I still kind of struggle, and every so often, I'll point toward a picture and refer to that function, and that's not good. Okay, I'll try to. Obviously, I'll try to be as careful as I can, but also I will try to point out and confess when I screw that up. Okay, here's a different kind of picture. Most people don't like this kind of picture as much as graphs. I think that's a mistake. This is, it's different. It's not better, it's not worse, it's just different. But this is what I like to call the literal picture. I am actually not clear that there is a formal name for this kind of picture, but this kind of picture is all over the place. You're going to see this a lot. So I'm going to call it the literal picture. It's just literally taking the domain and drawing that domain, taking the target and drawing that target, and then taking the suggestion again of this arrow as, stuff comes out of the domain and goes into the target, and literally just indicating like so that, look, stuff's coming out of here and going into there. It's pretty literally just drawing exactly what the function is doing. Right, there's no arbitrary choices here particularly. It says there's the domain, there's the target, and that's what the function does. Now, for example, you could talk about this point in the domain, and you could say what happens to that point, and well, maybe the output value is this point in the target. So we think of this point going to that output by way of the function. Fine. It is a kind of a picture of sorts. It is also kind of a letdown because you look at what I have drawn here and you feel like you have a good sense for what this function's doing. I mean, where's the shape? Well, how can I infer, I'm accustomed to being able to infer from slopes that means something, or, curvature, or I can infer something about the second derivative. We're accustomed to be able to have a shape that we can look at and make inferences from the nature of the shape. We have no shape to look at here. So it's a big letdown. But let me point out, while you might be thinking, yeah, I like graphs much better, that is an apples and oranges comparison. You're probably comparing this picture with this picture here. Well, no fair. This picture is for a function from R2 to R1. Right? This is a picture of a function from R3 to R1. If we're going to do an apples to apples comparison, head to head, literal picture versus graph picture, we've got to look and compare this to the graph of a function from R3 to R1, which of course, nothing. Right? So, when the alternative is nothing, not much for the win. Everybody see the point there? Okay. All right. So let me elaborate on the not much. Actually, I claim this is actually a really good picture in certain ways. So here's something we're going to be doing a lot of in this course. When we start talking about derivatives, we're going to have to make sense out of what do we really mean by a derivative, and that is a whole story that we're going to spend the rest of Chapter 2 on after today, and I guess probably tomorrow. We're going to have still preliminary stuff we'll be setting up, at least some of. But here's something we will be doing a lot of. What is a derivative? And the big idea of a derivative is that when you move the input, then the output moves also. All right, let's go back to single variable real quick. You look at this picture, big idea of a derivative, and here we think of it as being a slope of the tangent line. And the big idea, though, is that if there's an input change, then there is a corresponding output change, and you compare the input change to the output change. A good way to do it in this case is to look at the proportion, and the proportion we interpret as a slope, blah, 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 right? And so that's how we think of it here. But in general, a derivative is a relationship between input changes and output changes. Okay, well, in fact, this picture is pretty well set up to talk about that. Because if I look at this point A, I can talk about changes to this value. I could talk about, for example, maybe I displace in the domain, maybe I move by that amount. I got some vector representing how much I move in the domain. And there would be some resulting linear estimate. We'll talk about how to do this later. But given this change in the input, we'll be able to talk about the corresponding change in the output. And while, okay, fair, I don't really see like a slope or something, but I can at least draw what the derivative is supposed to relate. The derivative is supposed to relate these vectors to those vectors. Right, yes?
But what concept do we use to conceptualize like the change of vector?
Oh yeah, look, if this point goes to that point, and then if I move by some amount, and if I were to look at this resulting new point right there, that point would have some output value. And so that input change then causes some corresponding output change.
Vector subtraction.
Yeah. Displacements. The difference between 2 points, sometimes referred to as a displacement. Yeah. Is that satisfying?
Yes.
Cool. Yeah.
Can we get the R3 graph into something in R3 as well?
One more time.
We have a R3 graph here, and then we graph it into something that is also in R3 to graph something that is in R6.
So okay, now I'm gonna have to pick on you a little bit. You said the word graph.
Oh,
you see what I'm saying? Okay, now I know nothing personal, right? But that's everybody's got to combat this, right? I have to combat this myself. I've got more years of combating under my belt, so I'm more accustomed. But it's so easy to make that mistake. I just wanted to point that out for everyone. So that's exactly the kind of thing we want to be careful about. Now, I'm sorry, but say your question again, please.
So if there's an R3, like we plotted something in R3.
Yeah, from our domain.
From the domain, and then can we also plot something in R3 in the range?
Yeah. So if you want to have the domain and the target both be R3, yeah, absolutely. And so, for example, maybe, so let's see here, W, okay, I can't use X, Y, Z, I called that W, okay, so how about U, V, W, something like that. Right, so now we have a function from R3 to R3. And some input change would lead to some output change. Yeah, absolutely. Yep. And then again, this is a great way to at least draw the players that a derivative, whatever this critter is, that relates these things, right? And I'll leave that for later. But the thing that will relate input changes and output changes, I can't draw that thing, but I can draw the things that that eventual derivative relate to each other. Absolutely. And this is a great way to understand a function from R3 to R3. Totally. Okay. Right. Okay, so heads up, we're going to be using this kind of picture regularly. Here's another one. Level sets. Also a different kind of a picture. This is not a graph. This is not the literal picture. This is a third now way that we are going to draw pictures to represent certain kinds of functions. And pretty much the punchline, again, I have a definition written down if you want to see the formality, but here's the sort of, in practice, this is kind of the deal. The big idea of a level set is we take the value of the function and we set the value of the function equal to a constant. That's not what we did with graphs. With graphs, we took the formula for the value of the output value of the function, we set it equal to a new variable. Right? Here we would have called this z if we were drawing a graph. Level sets say, no, we're not going to call it a new variable. We're just going to set it equal to some constant and see what happens. And not hard to persuade yourself when you set the function equal to 1, that resulting equation is the equation of the unit circle. And if I were to set the value of the function equal to a different constant, let's say 2, well, that gives me a different circle, different equation, also a circle, different circle, like so. And so for each output value, there is a corresponding, what we call level set. We'll talk about why they call it a level set. Okay, yes?
So what do you mean by like the F inverse one?
Oh, yes, I'll get, momentarily. Is everybody, the notation I need to mention, is everybody okay with this concept to get the ball rolling? Yeah. Okay, great question about the notation. So the big idea here is I choose the output value that we're going to set the function equal to first, and then the result is I get the corresponding curve. So given an output value that I can, set the function equal to, given an output, I get a collection of inputs, and you just notice that the arrow is kind of going the other way. It's going sort of backwards. Now, this is an abuse of notation. It's a very common little math slang, right? Little math crime, right? We write F inverse. This function is not invertible. I don't mean F inverse literally. Yeah, but it sure is a convenient, sloppy to be fair, but it's a convenient way to communicate that, look, we're going to, if I say F inverse of 1, what I mean is take 1, set that to be the output, look for the corresponding inputs. Effectively, we're turning 1 into that curve. Is that satisfying? Yeah. So it's an abuse of notation, but very common, and it's one of these things where if everybody knows what we're doing and why it's not okay, then it's okay. Does that make sense? Yeah, so it's a little sloppy, but everybody knows what it means, and so it's all right. Okay. So here's a great example of a level set. Y'all may have seen these. I don't know how much hiking y'all have done, but if you ever go hiking and if you have what's called a topographical map, on the topographical map there will be what are called contour lines, and all these are level sets. So in particular, this right here is where the altitude function is equal to, some value. Let's say 100. I don't know. Maybe that's where the altitude is 100. Right? And then maybe this is where the altitude is 200, and then this is where the altitude is 300, etc. And so you can draw these, again, in hiking context, they call them contour lines. But they're level sets. We're literally taking a function, setting it equal to various different constants. And you kind of draw them all together, and it helps you get a sense of, roughly speaking, what's the shape of the mountain here? What are we looking at? Which way is uphill and stuff like that. So here's a nice example. I downloaded this topographical map from some appropriate government website. I've already forgotten, but this is. Obviously the world is full of mountains. I had a lot of choices of which ones to download. This is a mountain that I climbed when I was about y'all's age, and it was a family thing. And there's a lot of interesting stuff that you can infer about the shape of the mountain from these contour lines. And now keep in mind, each one of these lines represents a constant altitude. So some of these are even labeled. You can see like this curve, right? There's a label there that says 12,600, right? And then here's 12,200, and this is 12,000 even, right? And so you can kind of tell uphill is sort of like that. Uphill is the direction you go to increase altitude as fast as possible. And if you want to get from, let's say, that line to that line as fast as possible, you do it by going sort of across the lines. Right? So other things that you can tell, hopefully it stands to reason, when the lines are closer together, that means you're gaining whatever the altitude difference is between these contour lines over shorter distances. That means it's steeper. Right? Whereas when the lines are farther apart, you can gain the same amount of altitude, but it's over a much more horizontal distance, and so it's just not as steep. Right? So that's, again, you can kind of get a sense for how steep the climb is and what you're going to be seeing, what you're going to be looking at by looking at these contour lines. And I think it's also interesting to notice that the hiking trail here does this zigzaggy thing. Why do they do that zigzaggy thing? Well, I can tell you from personal experience, this is too steep for me anyway to just climb straight up. It's like this. Right? And it's a slog. It's brutal. But you can see that if you zigzag, I'm still kind of going generally the same direction, but by zigzagging, I'm distributing that altitude gain over more horizontal distance, so it's not as steep, and it's just a more reasonable, tolerable experience. So they call these switchbacks, and they do this a lot with these kind of trails. Yeah. How we doing? Everybody's all right? Okay. By the way, just so you know, how close the lines are there, that is so steep. When you're there and you're looking down, you'll be 100% convinced that is pure vertical. And it's not. It's only like it's like about like that. Right? But when you're up there and you're looking, let's see, what do we got here? That's 13.4. This is 12.2. That's over 1,000 feet down. Your perspective goes a little bit. Right? It's very disturbing. All right. Okay, let's see here. Let's get back into the thing. Looking at this example again, if you wanted to get from here to there, if you wanted to climb the mountain, right? Well, the naive take would be to go that way, and again, that's brutal, right? That's possibly even dangerous, right? Of course, I haven't labeled. I don't have any specifics. I don't have any scales here, so. We don't have that. But notice, here's what I would do. I would do the hike like that. And then notice I still get up there, right? But it's basically level along in here. And then look at how much distance I get to spread out the altitude gain between these two contour lines, right? That's not that steep, that's not that steep, that's not that steep. It's really not steep anywhere along in here. If I were to go straight up like that, it'd be ridiculously steep. So, without even seeing the mountain, this helps us understand and make good decisions about how to put together your hike. So, level sets can be a really good way to understand a function. We're understanding the altitude function here with a two-dimensional picture. And that's nice. Okay. All right. Now, there is a relationship between level sets and graphs. I cannot emphasize enough, they are not the same thing. Right? They are different constructions. The level set construction, the graph construction. You can see right here the difference when you're looking at a function. Right? We form the graph by setting the output values equal to a new variable. We form level sets, level curves, in this case, by setting the value equal to a constant. We get different equations. Same function. Same function. Different constructions give us different equations and give us different resulting pictures to describe the same function. Everybody happy? Okay, so a neat observation. I know this is just playing around with the algebra, but if I set f equal to z and if I set z equal to c, I mean, in effect, the punchline is to effectively set f equal to c. Now, that's just silly observation, right? But notice I can interpret this as saying that if I look at the graph, and if I then take a horizontal cross section, I claim this is a horizontal cross section, z equals a constant, right? This is z equals a constant. It's like taking a horizontal slice of that graph, and the result of doing both of these is that I get the corresponding level curve. And so altogether, that gives us this little punchline. Level curves are horizontal cross sections of graphs. And here's a nice explicit example. Look at this function right here, which we've seen before. Now I am going to have to make there's a little bit of a foreshadowing. We're not ready to justify the following quite yet. But if I were to take this function and talk about the graph of that function, again, set it equal to a new variable, z. If I were to draw this graph, I'm just going to assert, claim that a kind of a cereal bowl sort of thing, something about like that. I'll justify that very soon. Possibly today. I don't think we're going to make it, but early tomorrow. So that's what the graph looks like. Again, take my word for it for the moment. Let's think now, as indicated up here, if I were to take that graph, and if I were to take a horizontal cross-section of it, well, horizontal cross-sections, like so, right? Horizontal cross-sections. Well, then the function is equal to z is equal to c, so the function's equal to c, and I get these circles. And notice those circles are exactly the level sets of that same function. So this is what we're talking about when we say that level sets are horizontal cross sections of the graph. Everybody okay? Okay. All right, now again, got to be really careful about the terminology. It'd be super easy to be like, call this a graph or to call this a function, right? And lots of confusion ensues. You got to be extremely careful. And I know, again, you have these reflexive It's not your fault. Reflexive tendencies to say graph when you mean picture, or function when you mean equation. It's so easy to do. Try to retrain yourself. Speak slowly and consciously. Wait a minute. What do I mean here? What is that literally, formally called? Right? And then make your statement accordingly. And it is a tedious process to kind of retrain yourself in this way. But it's got to happen. Okay. How we doing? Everybody good? Okay. All right. Oh, by the way, if you catch me getting it wrong, please point it out. And you probably will. Okay, so here's a nice example of how these constructions are different. Now, what I've done so far is I've said, okay, if you give me a function, what are all the different pictures that we can produce of that function? Now, we talked about graphs and level sets and the literal picture. And there's also flashback when we draw a parametric curve. Notice, wait a second, when we draw a parametric curve, that gives us a picture. What kind of a picture is that? Is that the graph? Nope. Is it a level set? Nope. It's none of these things. So a parameterization is yet a different kind of a construction. So we're up to 4 different, like structurally, importantly different kinds of pictures that we use to describe different kinds of functions in different ways. And they all have different features. Okay, so that said, we're going to turn it around now. Instead of looking at one function and thinking about all the different pictures, we're going to look at a picture, a geometric object, I'm going to say this line, and we're going to talk about what functions can I use to represent that picture, not what pictures can I use to represent a function. All right, does everybody see how this is going to be a little bit different? So this line, just a line, right? No algebra given. This just a line in the plane. That's all it is. Purely geometric object. It is a graph of a function. It is also a level set of a different function. It is also parameterized by a third function. These functions are all different, right? So this function, whose graph is that line, this function, one of whose level sets is that line, and this function that parameterizes that line. All different functions. So let's just take a moment to appreciate how different these functions are. Not only do they have different formulas, right? Totally different formulas. They have different domains and targets. They're not only different functions, they're different types of functions. This one's R1 to R1. This is R2 to R1. This is R1 to R2. All different. Now let me try to persuade you that these are what I claim. Starting at the bottom, you can take this point as your x naught, and you can take this vector as your v. And if you use the chapter 1 construction, you know how to parameterize a line using that red point and that purple direction vector, you will get exactly that parameterization down there. Parameterizations are not unique. You could use a different point. You could use a different direction vector. Sure, all good. Different. You'll get different parameterizations. Fine. You could always lots of different ways to parameterize. Okay. All right. How is this a level set of this function? Well, that's a pretty easy one. This function, I think it's pretty easy to see that I will get this equation, namely I will get that line, if I just set that function equal to apparently 6 here. So you set it equal to 6 and boom, you get that line. Now sometimes it's Sometimes it's right there looking at you. It's handy. Anybody see how I did that? Okay. Now the first one, how I find the function whose graph is this line, a little trickier. That line, again, we've already discussed. That line is described by that equation. I need for that equation to be the same as what I get when I set some function. Let's assume we don't know what that is yet. I need to set that equal to y. So I need some function of x that when I set it equal to y gives me, I wanted to be in highlighter mode, gives me this equation of that line. And how am I going to figure out what to set y equal to? What is this thing that I set y equal to that gives me this equation? Another way to say that is take this equation and just solve for y. Right? If I were to take that y right there and solve for it, I would get that expression. So, again, sometimes it's a lot of finding the function whose level set, you take the constant right there looking at you, right? This one requires a little bit of work. Does everybody see how I did that though? All right. Okay, a matter of detail, important detail. To me, this is an important conceptual point. To y'all, this might be, if nothing else, a strategic point, right? Do keep in mind that on a question like this, when I ask for a function, and I'll usually specify, just to be ultra clear, but even if not specified, when we ask for a function is a trio. It's not just a formula. I need the domain and the target and the rule of assignment, right? So notice I didn't just say f of x equals blah, 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 right? We've got the domain and the target and the rule of assignment there. So that's what makes this a function. Everybody happy? Okay. All right, so take time as appropriate to persuade yourselves, not only that these, question.
So when you draw the level set, it'll be like, have this x, y, and then it'll translate to a horizontal axis.
Yes, yeah, that's right. So you're talking about this function here, right? And if I were to set that equal to various different constants, then what I would get is a bunch of lines, including that one, kind of like that. Yeah, that's right. So now the question says specifically the line L, right? So we're actually only interested in just that one line, but it remains that line is one of the level sets of this function. Yeah. Is that satisfying? Okay, so make sure to persuade yourself. Think it through. And again, I want to recognize this stuff is confusing. And it's confusing not because the algebra is hard. Algebra, right? Hardly nothing. Right? Algebra 1 level. We're not completing squares. We're not doing polynomial division, right? None of the hard algebra. Easy algebra. What makes this hard is be careful about the strict and proper use and interpretation of the terms. That's really the only hard part of this. But you do have to take that part seriously. That's what we're if this were an exam question, let me say that differently. This has been an exam question many times. You can look back at my old exams, right? They're all there. This kind of thing, not this exact thing, but this kind of thing has been a test question many times. And when students are answering those, what I'm interested in, what I'm testing, is do you know what these words mean strictly and properly, and can you interpret and use those terms accordingly, carefully, properly? It's all about being careful. So a common mistake that I get sometimes, for example, oh my gosh, it's just, it makes me cry a little bit every time. But if a student, instead of this, well, here, let me do it like this. If a student says, yeah, it's the graph of y equals 6 minus 2x over 3. Oh gosh. The student did the trivial algebra correctly. Yeah, sure. Trivial algebra is not the focus of this question. Right? This isn't a function. This is an equation describing the graph of the function. As written, the student is saying, yeah, this line is the graph of that function. And that's the Legos don't fit together. That's not what a graph is. Right? So don't give me the equation of the graph if I ask for the function whose graph it is. You've got to be careful with the interpretation and use of the terms. Does everybody see what I'm talking about here? Okay. All right. Okay, moving along. By the way, so it's worth recognizing. Why are we fussy about this in a multivariable calculus class? And it's because calculus is going to look different in all these different kinds of pictures. Y'all remember from Calc 1, y'all have seen a bunch of what I'm going to call the calculus of graphs. Derivatives, you have a geometric interpretation as slope. That's part of the calculus of graphs, because that applies specifically to graphs. Concavity, geometric concavity, right? That tells you about the second derivative. That's another part of the calculus of graphs. That too is specific to graphs. What we're going to be doing in this class, we will be looking not just at the calculus of graphs. I'll do it like this. Not just the calculus of graphs. We'll be looking at the calculus of level sets. It's totally different. Totally different. Importantly, really very different. We'll be looking at the calculus of parametrizations. Really different. And if you are not ultra clear on what the difference is, and for example, if you apply the calculus of graphs to a function whose graph isn't what we're talking about, then you're off in left field somewhere. This is a crash and burn situation. Nothing you're writing down makes any sense. It's all nonsense. So it's really important to be very, very clear about these distinctions because calculus applies totally differently for all of them. Okay, real quick little algebraic observation. This is super easy. Let's take a look at this equivalence right here. Super easy. Hardly anything happened. I just took the right-hand side of the equation and I subtracted over the left-hand side of the equation. Yawn. Right? No big. Here's the thing. This top equation is a graph. The bottom equation is a level set. Specifically, the top equation is the graph of a function here called f that has n input variables. The bottom equation is a level set of a different function with a different formula. This thing whose level set we're looking at is not f. It's y minus f. It's a function that has an additional input variable. Y is now one of the inputs to defining this function called g, one of whose level sets we're looking at. Totally different function. Right? But it is nevertheless kind of a nice conclusion, and that is every graph is a level set. And the reason we care about this, sometimes you will be looking at a graph of something. It'll come to you as a graph for whatever reason. And you'll look at this graph, and what you need to know about this graph is, oh golly, if only this were a level set. Man, the calculus of level sets would just get right on what I want here. If you're given a graph and you're like, oh, I want to use the calculus of level sets, boom, do this. Right? Take your graph that was given, do this little sleight of hand. Now you've got a function where you can say, hey, I'm interested in a level set of this function. You can apply the calculus of level sets to this function and get exactly what you want. So here's a quick example. Now you'll notice here's the sort of trivial algebra. Again, yawn, right? But we're talking about initially a graph of that function, but I can reinterpret it as a level set of that function. And so whatever this thing is here, if I want to understand it with the calculus of level sets, which I know we haven't done any calculus of level sets, we will very soon talk about calculus of level sets. This right here is the function to which I would apply the calculus of level sets to understand this graph. All right, it was a good stopping point. Y'all can read that little quickie observation. Calling it here. Y'all have a good rest of your Tuesday. Again, don't forget about the TA office hours. It's a free resource, right? No appointment necessary. Just show up. And hope y'all will take advantage of it. See y'all later. Have a good one.